In this section, we're going to talk about electrochemical cells. Now, most of you have probably already seen this in general chemistry too, at least most of it, but it's still worth revisiting this because it'll become a little bit important in the next section as well. So the main use for electrochemistry in the world around us is as sensors, and they are pretty much everywhere. So you've used some in lab. pH probes are electrochemical cells. You may think that, well, I'm just measuring pH, but if you really dig deep into it, pH is actually just a conversion of the voltage that the pH probe is measuring. So the probe measures a voltage, and that voltage is converted into a pH that you read using the pH probe. There are electrochemical sensors in car engines. They're used for blood glucose measurements if you're diabetic, and many other measurements are done by electrochemical methods. One more specific example of measurements using electrochemistry are a Chem 7 panel when a patient is brought into the ER. Now on the table to the right, you see a bunch of different components that are measured electrochemically. For example, sodium, potassium chloride, total carbon dioxide, glucose, and so on. So why would you want to measure these components? Well, the short answer is by measuring these different components in a patient, the ER doctors can easily determine or quickly determine if a patient is suffering from a specific condition. Now, when you're in an ER, what is the most important thing about making these measurements? Usually, if you're in ER, that means you need help right now. So speed is of the utmost importance, and electrochemical methods are good because they give results quickly. So the use of voltage measurements to extract chemical information, such as those in the Chem 7 panel, are best measured by what's called potentiometry or potentiometrically. So that just means using electrochemical method to measure the potential. Another word for potential is voltage. So an example of a potentiometric cell with zinc and silver is given on the diagram below. So this is obviously something that you might set up in a lab and nothing that would use to measure anything in a hospital setting. But as you can see, the electrochemical cell is separated into both an anode and a cathode. So the anode is on the left, the cathode is on the right, and each of the anode and cathode contain half of the reaction that has to be present in order for this potentiometer to work. So on the left-hand side, we have everything to do with zinc. We have the zinc 2 plus solution. We have the zinc electrode, which is right here. On the right-hand side, there's the silver electrode and the silver solution, and that is separated by what's called the salt bridge. And then up here is just where electrons flow, and the potentiometer is going to give us a voltage reading, which is the result of joining these two cells together. So the diagram on the previous slide just gave you a pictorial view of what that voltaic cell or galvanic cell would look like if you set it up in a lab. But usually when we're writing these on paper, we're not going to write out the pictorial diagram because it just takes too much room and it's too tedious to write out. So we would write what's called the cell diagram, and that is shown right here. So the cell diagram tells you everything you need to know about how this electrochemical cell is set up. We have components of the anode on the left-hand side of the cell diagram, components of the cathode on the right-hand side of the diagram, and then these two double lines represent the salt bridge, which is connecting both the anode and the cathode together. So if we were to write out the cell diagram for the electrochemical cell on the previous slide, we would write it as shown here. So we start off with the zinc electrode, which is the zinc solid, and this vertical line here represents a phase change. So we have a solid zinc electrode, and then the next thing that zinc electrode is in contact with is zinc 2 plus. So obviously we have a solid going to aqueous phase, so there's the phase change. And then the zinc 2 plus in the solution is in contact with the salt bridge. The salt bridge is then in contact with silver plus on the cathode side, and the silver plus is in contact with silver solid. And again, we have a phase change, which is represented by that vertical line. So when we're writing these cell diagrams, it's easy to go from left to right if you're looking at a pictorial diagram, and just say that the zinc solid electrode is in contact with the zinc 2 plus solution, which is in contact with the salt bridge, which is in contact with the silver plus solution, which is in contact with the silver electrode. So we're just going from left to right, what is in contact with what, and just writing it down in that order. So let's just try a quick example. You might want to pause the video to see if you can do this yourself. So write a line diagram or a cell diagram for this cell. Write the anode reaction, the cathode reaction, and the overall reaction. So the answers are actually on the next slide if you want to look at them, but try this yourself to see if you can do it. So what we want to do first is realize that by convention, these are all written as anode on the left, cathode on the right. So all we have to do is simply look at the anode side because that's where we're going to start. So we have cadmium first. Okay, that's the first part of our cell diagram. And then that's our electrode. There's a phase change between cadmium and cadmium nitrate. So the next component is going to be cadmium nitrate. Okay, we have our vertical line in between them representing the phase change. And the cadmium nitrate is in contact with the salt bridge. So there's our double line for our salt bridge. And now we're on the right-hand side, the cathode side. The salt bridge is in contact with KCl or Cl minus. In this case, we write it as KCl. You can write it as Cl minus as well, that's fine. And then the KCl, that's in contact with silver chloride on the electrode. So that's actually some solid that has precipitated onto the electrode. And then the silver chloride is in contact with the silver solid electrode. So this is how we would write this particular cell diagram. And now we're asked to write the cathode reaction, the anode reaction, and the overall reaction. So let's just flip over to the next slide and we can go over how to write those. So here's our cell diagram that we just wrote out in the previous slide. And now we have to write out what the reaction is at the anode and what the reaction is at the cathode. Now the anode reaction is always the oxidation reaction. The cathode reaction is always the reduction reaction. And when you're writing out an oxidation or reduction reaction, it's important where the electrons go. So oxidation means a loss of electrons, which means that you would have electrons as a product. Reduction means the gain of electrons, so you'd have electrons on the reactant side of the reaction. So if the anode is oxidation, we know that we have cadmium solid and cadmium nitrate. So we have cadmium solid going to cadmium 2 plus, and if we just stopped there, we would have a problem because our charges wouldn't be balanced. We'd have cadmium solid, we'd have cadmium 2 plus. So in order to balance the charges, we have to make sure to add the appropriate number of electrons to balance out the charge. In this case, we would add 2 electrons. Okay, so that's the oxidation reaction, cadmium solid in equilibrium with cadmium 2 plus and 2 electrons. Now the reduction reaction, we're going to start on the cathode, which is over here, the right-hand side of our reaction. So we're going to have, in this case, silver chloride making silver solid and chloride minus. Okay, this one's a little bit tougher to actually figure out just by looking at it. So this is not something that I would give you on an exam and ask you to figure out. The more simple ones are the ones that are like the anode. So cadmium 2 plus or a nickel 2 plus to nickel solid, that kind of thing. So ones like this, you can use your textbook and you can look up this particular reaction in the table of standard reduction potentials in one of your appendices in the book, and this is the reaction that would come out of it. Okay, so we have silver chloride plus an electron, right, because we have one extra negative charge on the product side, so we have to have a negative charge on the reactant side as well. So this is written as a reduction reaction because it's got an electron on the reactant side. The cadmium reaction is written as oxidation because it has electrons as a product. And now what we can do is we can try and write the overall reaction. Now the important thing to note is that the cadmium reaction has 2 electrons, the silver chloride reaction has 1 electron. And when we write overall reactions, we can't have extra electrons lying around on either side of the reaction. So we have to make sure we cancel out those electrons. So what we have to do is to make sure that we double the cathode reaction. So we want to have 2 silver chlorides, 2 electrons, 2 silver solids, and 2 chlorides. So then we can cancel out the electrons now because we have 2 electrons on the reactant side, 2 electrons on the product side. they cancel each other out, and now we can simply add the reactions together to get the overall reaction, which is shown on the bottom here. So when we're trying to determine the voltage of these electrochemical cells, we'll use something called the Nernst equation. And what it does is expresses the net driving force for a reaction. So whenever you're using the Nernst equation, you'll be solving for E, which is going to be in volts. So that's going to take into account voltages for two half reactions. So you're going to look at voltages for the cathode, the reduction reaction, and for the anode, the oxidation reaction. So these are half reactions, as we saw in the previous slide. So the cadmium solid going to cadmium 2 plus with 2 electrons, that's a half reaction. And the other reaction with silver chloride was also a half reaction. You can look up the potentials for these particular reactions in the appendix in your textbook. And the Nernst equation is kind of like the Henderson-Hasselbalch equation for electrochemistry. And the similarities are maybe not so obvious, but you know the Henderson-Hasselbalch equation has this relationship here. So it has the log of the concentration of products over reactants. And you can think of this kind of like the pKa. Okay, so E naught is the voltage that you would get for an electrochemical cell at standard state conditions, whereas E would be non-standard state conditions. And then this here is a correction factor that takes into account the number of electrons that are transferred in a reaction. Now, another way that it's like the Henderson-Hasselbalch equation is that when we have the concentration of B equals the concentration of A, what voltage do we get out of this reaction? So if B equals A, the log of 1 is 0. So this whole part of the equation ends up being 0. So when we have equal concentrations of products and reactants, the voltage of the cell is going to equal the standard voltage of the cell. So a couple other things to remember. Whenever you're using the Nernst equation, it's just like using any other equilibrium type calculation, right? The concentration of products over reactants, whenever we have solids or liquids, those are not included in the equilibrium expression, so they're not included in the Nernst equation. So only use pressures and aqueous phases in the Nernst equation. And if you have to multiply a reaction by a number, like with the silver chloride reaction, we had to multiply that by 2. If you look up the standard reduction potential for silver chloride, you notice that it has a specific number, but if you multiply the reaction by 2, the standard reduction potential does not change. So you don't have to multiply that standard reduction potential by 2, you keep it the same as it was. So if we have this particular reaction on top here, so we have P4 going to pH3, and we have a standard reduction potential of minus 0.046 volts. If we multiply that reaction by 2, in this case, so now we have half a P4, before we had a quarter of a P4, the standard reduction potential, or the E naught, does not change. So it remains the same. Okay, so remember when we're talking about these electrochemical cells, the reduction is the cathode. It's on the right side of a line diagram or a cell diagram. The oxidation is the anode, and that's the left side of the cell diagram. So when we want to figure out the potential of an electrochemical cell at standard state conditions, we will simply use this equation here, which is the overall voltage or the overall potential of the cell is going to equal the reduction potential of the cathode minus the reduction potential of the anode. And again, you'll find these in the appendix in your textbook. So here are some steps to finding the voltage of an electrochemical cell. So the first thing, write the reduction half reactions for both half cells and find the standard reduction potential, or E naught. Okay, use appendix C in your textbook to find these values. Multiply any of the half reactions by a number to make sure that the electrons are the same in both the anode and the cathode reactions, but again, don't multiply the E values by anything. Write the Nernst equation for the cathode. This will have the larger E naught value. So the reaction that has the highest standard reduction potential is going to be the cathode, and the Nernst equation that you write for the anode will have the smallest value for the standard reduction potential. Find the net cell voltage using this equation here, And then to write the balanced cell reaction, subtract the anode reaction from the cathode reaction, just like we did with the cadmium and the silver chloride reactions a few slides ago. Okay, so let's go over a couple examples to help clarify some of these concepts. So the first one, write the line notation, determine the overall cell reaction, and find E cell at 25 degrees Celsius of a galvanic cell made of an aluminum electrode in a 1 molar aluminum nitrate solution and a copper electrode in a 1 molar copper nitrate solution. So we're given some standard reduction potentials for both aluminum and copper. So if we're trying to first write the line notation, or the cell diagram, we need to know which of these, the aluminum or the copper, is the anode and which one is the cathode. So remember, the anode is going to have the reduction potential that is the lowest. The cathode will have the highest reduction potential. So that means that this is going to be the anode, the aluminum, and the copper is going to be the cathode. So now that we know which is the anode and which is the cathode, we can write the cell diagram. So again, we're going to start off with the anode components on the left-hand side of the reaction. And we always start off with an electrode, and electrodes are going to be solid. So since we have the anode on the left, the anode is aluminum, we're going to start off with aluminum solid. And then phase change, aluminum 3+ is going to be the solution that's going to be in contact with. Now we're done with all the components of the anode. We can write the salt bridge and then start with the components of the cathode. So the cathode is going to start off with copper 2+, because we're always going to have aqueous solutions in contact with the salt bridge, and then the only thing we have left is the copper solid. So that's going to be our cell diagram, and we're also asked to determine the overall cell reaction. So to do that, let's first write out two reduction reactions using aluminum and copper. So if it's a reduction reaction, we have to have electrons on the reactant side of the reaction. So for the reduction of aluminum, it's going to be aluminum 3+ plus 3 electrons going to aluminum solid. And for copper, we're going to have copper 2+ plus 2 electrons going to copper solid. So we know the aluminum reaction is actually an oxidation, but what we've written it as is a reduction. So when determining the overall reaction, one of these reactions has to be written as an oxidation. So we have to rewrite the aluminum reaction so it's in the form of an oxidation reaction. And to do that, we just reverse it. So we're going to have the aluminum solid on the reactant side, and then the aqueous products on the product side. Okay, now we're almost ready to add up the reaction. The one thing we still have to consider is the fact that the copper has 2 electrons in the reaction, whereas the aluminum has 3 electrons in the reaction. So in order to make them cancel out, we would have to multiply the aluminum reaction by 2 to make 6 electrons, multiply the copper reaction by 3 to make 6 electrons, and then when we write the overall reaction, we'll end up with 3 copper 2+ plus 2 aluminums solid going to 2 aluminum 3+ and 3 copper 2+. So since we multiplied the first reaction by 2, the second by 3, we have 6 electrons for each of the reactions, so the electrons end up canceling out, and remember that is a requirement for writing an overall reaction because we can't have excess electrons just hanging out in the middle of nowhere. So the last part of this question is to try and find the E cell, or the standard reduction potential at 25 degrees Celsius. So all we need to do now is to use the standard reduction potentials of each of the components, write out the reaction E cell equals E plus minus E minus, so the plus being the cathode, the minus being the anode. Our cathode, again, is the copper, so it's going to be 0.339 minus 1.677. Both of those are volts. So our E cell, 2.016 volts. Okay, you know it's right because it's a positive number. If you get a negative number, then you know you've done things backwards. Okay, so now let's go through an example at non-standard state conditions. So you know the other one was at standard state because it was both at 25 degrees Celsius and each of the components of aluminum and copper were at concentrations of 1 molar. In this case, we're also at 25 degrees Celsius, but we have concentrations of our components that are not 1 molar. So we know we're at non-standard state conditions. So in all of these types of calculations, we know we have to use the Nernst equation, and part of the Nernst equation is finding the standard reduction potential of the reaction. So just like we did in the previous example, we're going to use this equation here to find the standard reduction potential. E cell equals E plus minus E minus. So to do that, the first thing we have to know is which of these reactions is the anode and which one is the cathode. So remember, the anode is going to have the one that's the smallest value for E, and the cathode is going to have the one that's the highest value for E. So in this case, the one on top is going to be the cathode, and the one on the bottom is going to be the anode. So now if we simply write out our equation, we're going to have 0.22 volts as our cathode minus negative 0.402 volts as the anode. And if we complete the math, we get 0.624 volts. So now let's try and figure out what's going on with the Nernst equation. We've already figured out this part of the Nernst equation, but we need to know N, the number of electrons that are transferred in the reaction, and we also have to know the concentrations of products and reactants in order to figure out the E cell at non-standard state conditions. So the first thing we're going to do is we're going to write out the reactions in the appropriate form. So one reaction has to be written as a reduction, the other has to be written as an oxidation, and since the oxidation reaction is the one that's the most negative, that's going to be cadmium, and oxidation reactions have to be written in reverse because what you'll be given is a reduction reaction. Okay, so whenever you're given these values on top up here and given an E value, those are standard reduction potentials, which means the reaction is written as a reduction. But since one of them has to be oxidation, we have to reverse one of these reactions, and we're going to reverse the cadmium reaction because that is the oxidation reaction, it's the anode. So we reverse that one, we keep the silver chloride one the same. Okay, that one doesn't reverse because that's the cathode or the reduction reaction. And the next thing to realize is that cadmium has 2 electrons, whereas silver chloride reaction has 1 electron. So we have to multiply the silver chloride reaction by 2 in order to be able to cancel out those 2 electrons that are on the cadmium reaction. So now we can add up the reaction. Okay, our electrons are going to cancel out. So we have 2 electrons here that will cancel, 2 electrons here that will cancel, and we simply just write down what we have remaining on the left and what we have remaining on the right, and we end up with our overall reaction as shown here. So what this tells us now is what we have for our products and what we have for our reactants. So the important components in these reactions is again going to be the aqueous components. Remember, solid components and liquid components are not included in the Nernst equation or any equilibrium type equation, which is part of the Nernst equation. Right? That's this part right here, concentration of products over reactants. So it turns out that we have chloride minus as an aqueous phase and cadmium 2 plus as an aqueous phase, and those are both products. And notice that we have no aqueous components on the reactant side. So in the question, what we can see is that we have 0.5 molar chloride and 0.01 molar cadmium. So when we write out the Nernst equation, our E cell we already figured out in step 1. The number of electrons transferred in the reaction is 2, right? Because we needed to have 2 electrons in these half reactions in order to be able to cancel them out. Now for our products, we're going to have 0.5 squared times 0.01. And remember, we have to have the squared on the 0.5 because the concentration of Cl is 0.5 and there are 2 chlorides in the reaction. So that means we have to square it. So if we solve that equation, we end up getting the voltage of the cell being 0.701 volts. Okay, so the last quick example I have here is to choose the correct cell diagram that represents a cell composed of the 2 reduction half reactions shown below. So we have gadolinium and magnesium half reactions. The gadolinium half reaction has a potential of minus 0.549 volts, and the magnesium has a half reaction of minus 2.36 volts. So as usual, we have to know which one of these is the anode and which one is the cathode. and the smallest one is going to be the one that's the anode. You could also think of it as the one that is the most negative is going to be the anode. So this is the anode, which means that this would be the cathode. So when we're writing cell diagrams, the anode has to go on the left side. So we know that we're going to have magnesium on the left side because that's the anode. So it's either going to be A or C. And whenever we're writing line diagrams, we know that we have to have the electrode being the first part of that line diagram. So we're going to have a solid first. So the answer to this question is going to be A. So that's all I have for this section. If you have any questions, please let me know.